Good morning, champ. Now that we can approximate multivariable functions with Taylor polynomials, it's time to ask an important question. Where do these functions reach their highest and lowest points? We're talking about local and global extrema, the peaks, valleys, and saddle points of a surface. This topic connects everything we've learned about gradients and the Hessian matrix. In single variable calculus, extrema occur where the derivative equals 0, where the slope flattens out. For a function of several variables, we do the same thing, but we use the gradient vector instead of a single derivative. The gradient is the vector of all first partial derivatives. A point is called a critical point if the gradient equals 0. At that point, the tangent plane is flat. There's no slope in any direction. To classify a critical point, we use the Hessian matrix, which contains all second partial derivatives. We compute its determinant, d equals f double x times f double y minus open parenthesis f sub xy close parenthesis squared. This number tells us how the surface bends near the critical point, whether it curves up, down, or does both. Here's the second derivative test. If d is greater than 0 and f double x is greater than 0, we have a local minimum. If d is greater than 0 and f double x is less than 0, we have a local maximum. If d is less than 0, we have a saddle point, up in one direction, down in another. And if d equals 0, the test is inconclusive. We'd need higher order terms. Let's test it on f of x and y equals x squared plus y squared. Compute the partials. F sub x equals 2x, f sub y equals 2y. Setting them equal to 0 gives x equals 0 and y equals 0. The Hessian is a 2 by 2 matrix with 2's on the diagonal and 0's elsewhere. The determinant equals 4, which is greater than 0. Since f double x equals 2 and that's positive, the origin is a local minimum. And because the function is never negative, it's also a global minimum. Geometrically, it's a perfectly symmetric bowl. Now take f of x and y equals x squared minus y squared. Compute the partials. F sub x equals 2x, f sub y equals negative 2y. Set them to 0. X equals 0, y equals 0. The Hessian matrix now has a 2 and a negative 2 on the diagonal. The determinant equals negative 4, less than 0. That means the point is a saddle. It curves up in one direction and down in another. You can imagine a horse saddle or a hyperbolic paraboloid. Next, try f of x and y equals negative x squared minus y squared. F sub x equals negative 2x, f sub y equals negative 2y, so the critical point is again at 0, 0. The Hessian has negative 2's on the diagonal. The determinant is 4, which is greater than 0. Since f double x is negative, the point is a local maximum, the top of an inverted bowl. Now let's talk big picture. A local extremum is a high or low point nearby. A global extremum is the absolute highest or lowest point on the entire domain. To find global extrema, especially when the region is closed and bounded, follow 3 steps. First, find all critical points inside the region. Second, evaluate the function on the boundary. And third, compare all the values. The largest is the global maximum, and the smallest is the global minimum. For example, f of x and y equals x squared plus y squared on the region where x squared plus y squared is less than or equal to 1. Inside, the gradient equals 0 at the origin. That gives f equals 0. On the boundary, where x squared plus y squared equals 1, the function equals 1. So the global minimum is 0 at the center, and the global maximum is 1 on the circle's edge. Let's summarize. The gradient equals 0 means a possible extremum. The determinant of the Hessian decides the curvature type. D greater than 0 and f double x greater than 0 means local minimum. D greater than 0 and F double X less than 0 means local maximum. D less than 0 means saddle point. And global extrema come from comparing interior and boundary values. So local extrema tell you where the surface bends, and global extrema tell you where it truly peaks or bottoms out. Together, they reveal the full shape of your function.